Hello everyone. Thank you everyone for coming. Thank you to Mr. Rokos for funding this. And thank you to the mistress. So, my name is Giovanni Bernardi, known as Gio, and I'm going to be talking about chemical weathering, that is the interaction between rocks and the atmosphere in a catchment in Peru. Now, before we start looking at Peru, this word climate is, everybody hears about it these days. We hear about it with regards to the warming of the oceans, with regards to CO2 storage, warming of the summers, and also our hops denaturing for beer, and obviously that's the biggest issue. And most of us will have seen a temperature time graph of some sort. Just to give you an idea, this is temperature average of 1990 as a zero line, and most of us focus on these few years here, these last 20 years, and these are the projections from the IPCC showing the temperature increase. But what I'm focusing on is something quite a lot more distant, something 60, 50 million years in the past. And you can see this line here, this green peak, and it decreases, and that's thought, scientifically, to be due to the Himalayas forming and uplifting, and the idea is that their formation and uplift is related to chemical weathering, this interaction between the rocks and the atmosphere, and that causes CO2 to decrease in the atmosphere. Now, why am I talking about the Andes? Because fundamentally it's a bit overlooked. As a mountain range that uplifted in a similar time span, give or take 10 million years, it's, it's something that's important to look at and something that hasn't been done very much yet. And so our project is looking at the interaction between silicate rocks, stuff like quartz, and carbonate rocks, stuff like chalk, and the interaction of them with two primary acids that are the dominant reactions of chemical weathering. And you can see from, I think that's quite simple schematic, that the interaction of silicate and rocks and carbonic acid long-term intake CO2, and carbonate rocks and sulfuric acid long-term release CO2. This is a very simplified schematic. I'm sure the earth scientists will be, tearing their hair out, but roughly that's sort of what that means. And so we're looking at the Andes because it's a very interesting catchment. To give you an idea, this is South America, that's Peru, and that is the particular part where my director of studies, Dr. Morag Hunter, went and collected the samples. So if we look at the overall geological setting of Peru, it's called subduction, means that one plate slides over the other, and then the one that slides under heats up, and then that forms the mountain ranges. And this is the catchment where Morag went and collected her samples. So on the right is the catchment map where all of the samples were collected. What she did is effectively she got a bucket of water, put it in the river, and then filtered it and put it through some quite fancy machinery to get the samples. And on the left is just a cross-section showing the geology. In the north, we've largely got those carbonate rocks that I was talking about, so chalk, and in the south, we've got silicate rocks, that's volcanic igneous stuff. And it's important because we know what reactions they're controlled by, and that's fundamentally what we're looking at. So just to give you an idea of the results, here's a plot from a pretty famous paper, chemically speaking, showing the 60 largest rivers in the world. Now, the axes aren't necessarily that important, they're just controlled by the reactions, and they're important because the graph is important because you can see that the silicates and carbonates plot quite differently, and it's quite a nice mixing line. Now, when we put our samples on there, this is the Rio Cañete, and you can see that in one river, you actually get pretty well the whole distribution. So that shows why it's so important that we actually go and look at this from a geochemicals perspective with a view to CO2 intake, because actually it's quite striking how varied the water sort of chemistry is. And so right now, I'm just going to take you through what's called the chemical weathering model. So that's how we rationalize this whole intake exhaust business. So if you can imagine a river flowing downstream, you take a drop of water. That drop of water will be divided into 5 primary constituents that contribute to its chemical signature. So you've got rain, silicate, carbonate, evaporites, that's stuff like salt deposits, and human influence, anthropogenic influence. Now, we don't want human influence because we don't want any sort of anthropogenic things messing with the silicates and carbonates, so we remove, for example, the agricultural plains in the south that the river is flowing through. We don't want rain and we don't want evaporites because we only want the silicates and carbonates, which we know the reactions for, and those are that right there. And to remind you, this is how it works. So the silicates largely are responsible for the intake of CO2, and the carbonates are largely responsible for the release of CO2. So what does that mean? That means that now we can take our chemistry and we can assign a number of moles to the CO2 and see a short-term and long-term budget. So we can see that actually for the river in the short term, we've got intake. The line is largely negative for CO2 flux. That's a mass per unit time. But actually, for long term, that's tens of millions of years. Short term is tens of years. For long term, you see quite a lot of CO2 exhaust. Now, if we take this to a slightly more detailed level, if we look at what's called the specific flux, it's a mass per unit time per unit area, you can actually start to compare it to other catchments. That's obviously important because you don't want to, if it's releasing CO2, how much CO2 is it releasing? So if we look at our catchment, this is a rough schematic map. In the north, you've got carbonates. In the south, you've got silicates. And we want to look at that point there in particular because we're summing cumulatively all of the chemistry from the top to the bottom. And as you can imagine, the water that comes from the top influences the one at the bottom. So we look at that point and we see that roughly we've got 500 kilograms of CO2 per kilometer squared per year, long-term CO2 release. What does that number mean? It's not very big because for a catchment of a similar size, you've got roughly 10,000 times more kilograms of CO2 per kilometer squared per year. So all in all, concluding, what does this mean? It means that our catchment is, over the long term, releasing CO2. And it means that for the Andes, for this particular mountain range, actually it's not quite as simple as the Himalayan story. And so it rewrites our thinking of habitability at the time because we've just attributed that to the Himalayas, but if the Andes are uplifting at the same time and releasing CO2, what does that mean? So more work is required, particularly in more Andean catchments, to refine the model. But it's quite a striking surprise, and that's sort of the idea of my internship. Thank you very much.